Okay, guys, good morning to everybody. Just sent you this by email. I'll show you here. GC mass spec, only one sample. I'm not going to be able to run GC mass spec of every one of your samples. Okay. I just was able to get one done. Okay. I don't have a TA. I ran the poster children's sample. This is your actual sample. This is a GC mass spec. Gas chromatography is usually coupled with mass spec. Gas chromatography, it's a type of chromatography. In lab, you're doing thin layer chromatography. That's a type of liquid chromatography because that refers to the mobile phase being a liquid. Gas chromatography, the mobile phase is a gas. Okay, it's on a column and it's usually a big instrument, expensive instrument. And so you inject your sample and it goes to the GC and that separates any components. If it's pure, there's only one component and there will be nothing to separate and it just gives you one peak. If there's multiple components, here's the GC of your sample. You have two major peaks. We also have a couple of slight baseline small peaks here. Okay? So multiple peaks. Then, as each peak comes out of the GC, it's sent to the mass spec. And you get a mass spec of that compound, which is now purified because this is retention time. This is how long it's spent on the column. This only spent 5 minutes on the column. At 5 minutes, it came out, hit the GC, hit the mass spec, but it came out as one thing. That didn't come out until 6 minutes. That didn't come out until 7 minutes. This came out at 9.5 minutes. But when it came out, it was one thing. And then some things came out later. Okay. Then you can get mass spec of each thing. For example, this signal here is like 9.5. Retention time of 9.5 minutes. You can click on that and get the mass spec of 9.5 minutes right here. See, this is the mass spec of what was coming out at 9.384 minutes, which is basically under there. Here's your mass spec. Okay? I gave you this because you're not running the instrument. That's what you want to sort of interpret. Here's something very important. So, is the compound pure?
No.
Two major components. Some minor, very minor components. But hold on, GC, whenever you run a mass spec, you have to dissolve the compound in a solvent. Well, the solvent's there too. The solvent's going to give a peak. Well, guess what? One of those is solvent. Well, here's a GC of just solvent. This is there because you added the solvent. So you subtract these signals from your other one, then you say, what was just there from my compound? Well, you see something's missing here. Actually, that huge peak, that must have been from your compound because it came from solvent. So that's why I gave you a mass spec of that one. Now, there's also nothing out here, so what was out here must have also not have been from solvent. So you know when you do an IR and it does a background? See, that subtracts out background for you. What's the background? It's running an IR of air. O2, nitrogen, CO2. But then the instrument cancels it out for you. Here you got to cancel it out manually by looking at one spectrum and canceling it out from the other. Okay, I sent you one file. Both of those are in that one file for interpretation. Now, only you can say that's your compound. Everybody else is going to have to just interpret that as if that was yours. Okay? You can still interpret it. That's a common outcome for the synthesis, but it's just not going to be yours. But you can still interpret it as if it's the common outcome. If you have any questions, please let me know. Okay. So that group report is due Monday, Tuesday. What lab do we want to do on Monday, Tuesday?
Williamson ether.
Williamson ether, why?
It looked interesting.
Good answer.
It did.
Using the carcinogen diethyl sulfate.
Oh.
Feels alder, Williamson ether, shaken, not stirred. National Martini Day is June 19th. You didn't know it was June 19th? Yeah, National Martini Day. I think it's the 19th. Yeah, it was the 16th. The 16th is the anniversary of Faraday reporting the discovery of benzene. It's tomorrow. And I'll send you a little blurb about that if you're interested in reading some of his own words as he describes his distillation.
It's riveting, huh?
Looking for pure fractions. Okay, where's the handout? Substitution reactions, hugely important. I think more important than alkene reactions to me. Hugely versatile. Okay, we're trying to do two different mechanisms for our example reaction. Example reaction. If there's anything outstanding, we'll discuss it at halftime. Okay, we did yesterday, we said, okay, the bromine's got to leave. We can just show that like this, right? We did that, we did boop, boop. We make carbocation plus Br minus. That's what that arrow gives us, yeah? The problem is, well, then this could, what, attack here? Oxygen makes bond to carbocation. There you go. That could be a possible mechanism. How many intermediates? Just one in terms of our main substrate. I mean, it's or one intermediate. Okay. Here. We don't like primary cations, yeah? Let's do a reaction coordinate diagram for this. What would it look like if this was the mechanism? Reaction progress, yeah? Some type of energy. Starting, bromide. Let's just put it somewhere here. Okay. Product, higher or lower? Not as easy to tell. When we went from alkene to, when we went from pi bond to sigma bonds, it was easier to tell because we went to stronger bonds. Here we're replacing one sigma bond with another sigma bond. It's much more difficult to tell what it is. It really doesn't matter. We don't need to try to tell if it's hard. I'm just going to put it about the same. That's supposed to be the same. Okay, one intermediate. Right here. Where is it compared to these two? Yeah, up here, correct? Is a charged carbocation. Now, if it was secondary, it'd be a little lower. If it was tertiary, it'd be a little lower. Okay, so here we go. What do? Settle into some well. Now we're falling downhill. It doesn't take much energy to fall downhill. It's just a little bit of transition state energy and boom, you're downhill. Here's your intermediate. What's the rate determining step?
First step.
First step, why?
It's the highest peak.
What's the greatest activation energy? Usually forming the carbocation. Okay? So if we did this, the first step would be the rate determining step. Then the second step we would call what?
Fast up.
Fast, yeah, fast compared to the slow rate determining step. What happened in the first step? What's a general term for what happened?
Substitution? Well, no.
Leaving group left.
Leaving group left. That's 3 words. What could be one word for what happened?
Substitution?
Ionization. The bromine just ionized off. Right? What happens if you put HBr in water? The bromine leaves and it gives H plus Br minus. And you call this process ionization. Yes, ionization of the leaving group to form ions. Okay, so the ionization here is the rate determining step. What's the second step? How would you describe that? the overall things of substitution. Nucleophile attacking. Okay? Nucleophilic addition to carbocation. Okay? Often I'll just say that the nucleophile adds. The nucleophile adds. Nucleophilic addition. So terminology. So when you're out tomorrow night, you can discuss these. Okay? All right? Everybody know, we go same lingo. All right. So, this is called an SN1. Why SN1 versus 2? What does the 1 mean? No. 1 refers to the number of the substrates. Both of these considered reagents or substrates. The number of those in the rate determining step. Here's your rate determining step. Is the alkyl bromide involved in the rate determining step? Certainly, it's undergoing ionization in the rate determining step. So that's 1. Is the hydroxide involved in the rate determining step? No. It's only one thing involved in the rate determining step. Substitution by a nucleophile unimolecular. That refers to what's involved. Okay? Only the bromide. Now, we'll talk about changes in concentration. How do you speed this reaction up? Will you ever make this reaction faster by adding more hydroxide? Why not? It's not involved in rate determining step. Why would adding more of that change the rate? Do you understand what rate determining step means? That may make the fast step faster, but guess what? Making the fast step faster ain't going to change your overall rate. The rate determining step is the one you got to change to affect the rate. Because it is rate determined. It determines the rate. Okay, there's an SN1. The mechanism is not SN1. Now, most professors will cover one mechanism for a week or a day here, and then cover the next one. I cover both at the same time. Then we sort of focus on one and focus on the other. I'm introducing them both. It's not this. Mainly, why is it not this? Because the primary cation is bad. Okay, let's look at SN2. What's another way we can show this mechanism? What's another way we can get these bonds broken and bonds made? But different from that, because obviously if we did the same as that, that would be called an SN1. What's another way we could do this? And the other way is sort of what we've done before with some alkene reactions. That is, what if these electrons just came in here and kicked that off? Have we ever done something like that? Okay. What if we just did this? What would this arrow movement mechanism give? That. That's it. Right? Hydroxide making bond to carbon. There you go. What does this arrow mean to you? Bromine leaving, and the long pair moves on. There you go. That's a different mechanism, isn't it? Did we ever make cation here? No cation here. Okay. How many intermediates here? None. What would this look like? Any intermediate?
No.
What would it look like? It would look like that. So some type of activation energy leading to the other one. By the way, when we showed reaction coordinate diagrams, we showed one like this, and I said no intermediate. Look back at that. I probably even wrote SN2 on it. But, yeah. Okay. Which step is the rate determining step? That one. Because it's only one step. Okay, so that's got to be the rate determining step right there. How many of the substrates are involved in that rate determining step? Both of them. Two things. 1 and 2. That's why it's called SN2. When we have two things happening at once. See up here, I only drew one arrow at a time. Here I'm drawing two arrows at once. What do we call that when things happen at once? Bonds break and form, or a lot at once. The Diels alder was all at once. Because all three bonds are making concerted. Okay? Okay? Concerted. Concerted. Okay, how does this attack? That is, if the bromine is one way, how does the hydroxide come in? Backside. We really already talked about this. We just did not call it SN2. Concerted backside attack. This is essentially a description of the mechanism we're doing here. Call it SN2. Which mechanism do you like better? Making a primary cation or doing it like this? This is actually the mechanism for the model example reaction, SN2. Mainly because you never want to make a primary carbocation. Okay? This is it. Okay. You got to be careful. It looked like it was one step. In the future, we may see multiple steps and call it SN2. That's because sometimes this requires sort of an activation step or something. What is always one step is the actual substitution is always one step. It's a concerted substitution, backside attack. Determining mechanism by kinetic studies. Kinetic studies have shown that the rate of the above reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. You can change the rate of either one and you can affect the rate. You can either increase one of those. By the way, if you increase one of these, the rate will increase because it's becoming more concentrated and that's more likely for one molecule to interact with another, right? And if you decrease the concentration of these, you will decrease the rate, right? But evidence, you can go in the lab and determine this, the evidence of that reaction shows that either one affects the rate. So since the rate depends on both of the substrate, each must be involved in the rate determining step. We've already really said this. And thus the reaction is called bimolecular. It's SN2. We've already really discussed that up here. We also know that the rate is first order with respect to each substrate. One of each. Thus overall, the rate equation is second order and is written as follows. The rate of this, since we know it's SN2, and that's what it describes here, is going to be some type of constant times the concentration of this reactant times the concentration of that reactant. They're both involved in the rate determining step, SN2. Now, the rate is going to vary depending on different things. Here, the rate would be this. We learned about rates and rate units in Gen Chem. So that's a rate in molarity per second. Something per second? Okay. Chain. Okay. Reaction coordinate diagram for each mechanism. We already did that. Which mechanism matches the kinetic observations SN2? We've already answered that. What is the rate equation for the other mechanism? What would the rate equation be for the
Just bromonium.
SN1?
You leave the hydroxide out.
Yeah, we read
Yeah.
this.
Yes, just the alkyl bromide. Okay. That is, you're only going to get a change in the rate if you change that. because that's the only thing involved in the rate determining step. Like I said earlier, you could change the hydroxide in that SN1 all you want, but that ain't going to affect the rate. It's not in the rate equation. This is concentration alkyl bromide. What is K really? What is all involved with K? If that up there was forming a secondary cation, would the reaction be faster?
Yeah.
Yes, easier to form a secondary cation.
Oh,
Would be faster. How does that show up in the rate? We didn't change the alkyl bromide.
this is a rate, this is
That's in K. K is some constant. K comes from just the parameters of the reaction. The reactants. Okay? There's a lot involved with K. But then you can also vary that by changing concentrations of things. Okay? Now K would have to be, determined, etc. But usually we look at what a change in concentration of things will do in addition to K. Okay, let's get more specific here. Proving, now a lot of this will hopefully be redundant and we should know the answers to these things. But we discussed some of this in the alkene chemistry. Determining mechanism by stereochemistry. Let's look at this reaction. It's very similar except we got an extra carbon. We got some stereochemistry. If you react this substrate with KOH, we can get a substitution reaction to make KBr. I've just included the K here as a spectator ion. All right? This reaction is known to give complete inversion of stereochemistry. That is, if this is R, you get S only. So this reaction is an antioselective. The first one we've ever seen that's an antioselective. Of course, we start with one enantiomer. This product is optically active. Well, remember, you cannot create optical activity out of the blue. This can only be optically active if this is. And is that optically active? Yeah. So we didn't create optical activity out of the blue. Okay. Question. Is an SN1 mechanism more or less likely for this reaction compared to the previous one?
Less.
The question is a little bit vague, depending on why do you need
Because
less?
you're going to form a carbocation and the hydroxide can attack it
you're
from
looking
either
at
direction.
stereochemistry.
Yeah.
It's not a good question because you're focusing on stereochemistry. Focus on carbocation. What type of carbocation would be formed here? Secondary. Is that more likely than the primary?
Yeah.
Yes. Yes. Secondaries are possible. They're not the best, but possible. But which mechanism is this reaction? SN1 or SN2? And how do you know?
SN2.
How do you know it's SN2?
because the SN1 reaction would give both enantiomers.
Correct. If this made cation, the hydroxide would then attack. How do you attack carbocations? Either side. That's not the outcome here. We got inversion. How do you think you get inversion? It starts with a B.
Backside.
Backside attack gave you inversion. Because look, if the leaving group is back, and you do an SN2. When you do an SN2, what happens? The leaving group leaves, then you make, no. SN2 is concerted. You be the nucleophile. Boom! Hold your bond up there. Do it again. Okay. This bond was back. The new one is forward. That's inversion. Okay? That's what we got here. The bromine is back. The new group is forward because SN2. Okay? This is still SN2. But SN1 was more likely here. This actually could have been either, but the way I showed it, it's got to be SN2 based on the stereochemical outcome. So we can determine a mechanism by assessing the stereochemistry if we know the outcome. Or, on the other hand, if we were told this is SN2, we should show inversion. Why, how is inversion obtained? We'll do this from scratch. I'll look at the 5-coordinate SN2 transition state. Okay, let's redraw this compound here. The bromine like this. We got a methyl, an ethyl, and an H on the carbon as well. There's the ethyl. We got to make sure it's R. Let's see. For it to be R, BR, ethyl, methyl, I need the H coming forward. I'm going to draw the H forward. And the methyl. Back. Yeah, bring back. Let's draw this a little bit differently. Let me let's draw this down. There's the ethyl. Let's put these two. We want the methyl forward. Let's put it like this. And let's put the H back. This may work better. Is that R? Bromine, ethyl, methyl, clockwise, H in the back. It looks like R.
Yeah.
Okay. If that's drawn like that, here's the carbon, the bromine is this way. Where does the OH come in from? It's coming from the top, bottom? No, it comes in from here, correct? The bromine is that way. Opposite of the leaving group is this way. So this comes in here. And when it comes in, what does the transition state look like? Because that's what that transition energy is. It's where this is starting to form, and that's starting to break. So let's try to draw that, the transition state. We might need to call that carbon to kind of, perhaps, maybe not, but I'm going to call it carbon just to give us a starting point. The bond to the bromine starts breaking. The bond to the OH starts what? Starts forming. What happens to these groups? These are supposed to be eclipsing. The methyl is right in front of the H here. This is a forming bond. That's a breaking bond. Charges. First off, let's look at where we're totally going at the end, and let's come back and look at this. When it gets through, it's going to end up what? We're going to have a total new bond to OH over there. It becomes a full bond. This is now gone. Here's our final outcome. This is the transition state. Okay, also sometimes called what? Activated complex. Sometimes drawn with like daggers or something on the upper right. What's charge here? By the way, we had charge here, we create plus Br minus. The electrons totally move on to the bromine. Does this thing have any charge?
Carbon's gonna.
Hydroxide goes from negative to neutral in the product. What is it when it's partially bonded?
Partially negative.
It's partially negative. It doesn't become clearly neutral, because right here some of the electrons are still with the oxygen. What's the bromine here?
Partially negative.
It's also partially negative, because as it starts breaking, it takes on minus, but it's not full minus until it's totally broken off. Over here you got a full minus. Over there you got a full minus. The net charge of this is what?
Neutral.
No,
No, negative.
full minus. You got two minuses adding up there, okay? The charge is delocalized in the complex, so there's less of a full minus.
No, I mean, carbon would be partially.
No, carbon's got 3 bonds and then a half and a half. It's not like it's got 4 bonds. But look at this carbon. First off, these groups. These 3 groups are sort of this way. Tetrahedral. We see the tetrahedral. There's an ethyl, a methyl, H green, bromine purple. Let's see. Ethyl in the plane, methyl. If we said H was green, we're going to switch these two. This is in the plane. That don't matter how that's rotated. Bromine is what do we say bromine was? Purple. H is green. Methyl forward, H back. Ethyl's down in the plane, bromine this way. There it is drawn on the board. Okay. These 2 groups are going that way. I didn't draw it quite right. Actually, I did. If I draw the bromine there, these 2 groups compared to the carbon are coming this way. So, okay, they're coming this way. It's almost like those 3 are kind of like my fingers going that way. What happens when the nucleophile comes in? It comes in and it makes these fingers straighten up. And that's what I'm showing here. All things are flat now, and this is supposed to be eclipsing. Okay? And that's when it's. Then when it fully comes in, what does it do to these fingers? It pushes them this way. Okay? So it comes in, pushes them out, but then they go this way. Look, the methyl's forward. It just gets pushed forward this way. But that's inversion. Because if you look at this, this is R. But if you determine this here, that should be S. Yeah, see, that's S. Inversion happened. Okay? This guy here. What's the 3 groups on the carbon, not the partial, are planar here. 3 groups planar. That sounds like trigonal planar. Okay? The transition state is trigonal planar. Here. What are bond angles of trigonal planar? .120 degree bond angles. between groups here. What were the bond angles over here between groups? 109.5. Now, something that's sp2, that's the hybrids. What's left over on that atom that's not hybridized? One what? One p orbital, right? The p orbital would be perpendicular to that trigonal plane. Look at this. It's almost like that could be a p orbital there. That's the SN2 transition state is a lot like an sp2 in the p orbital there. And if it's sp2-like, this implies bond angles here. This is important because that can influence reactivity. These groups have to be able to achieve 120 in this transition state. If they can't achieve 120, the reaction may be difficult or very slow. Okay, this is inversion. It involves an sp2-like transition state. Kind of looks like this. It says it right here, sp2-like character. Application of this, right here. If you look at these two reactions, if you substitute this bromine with iodide, okay, first off, you got to get used to spectator ions. Here's what I recommend when you see a spectator ion. Get rid of it. What's the charge of the I? Yeah, this is iodide. You cannot go to the stock room and say, just give me iodide. You got to get something with it, like a potassium or sodium. Okay? So, we can iodide. SN2, that means the mechanism is what? These electrons come in here, kick that off. It's backside. We're not really showing any stereochemistry, mainly because it's not chiral. So you just substitute it. The rate for that is 1. If you do it with this guy, the rate is much less. That's a lot slower. Why is the reaction so much slower for this guy? Because what type of bond angles does the carbon have to achieve when it undergoes the reaction?
120.
120. Right now it's 60. Can that angle move to 120? Why not? It's fixed in this ring. You're like, hey, elbow, you need to move to 120. And the elbow's like, I ain't doing it. Unless you want me to break my, okay? So this is an application of understanding the transition state. Apparently it does it some, but it's slow. That's because there's wiggle room. Just like in Gen Chem, you learn 109.5, and then you talk about how ammonia is really 103 or something. Okay. This is sort of the standard. We can get some wiggle room. This is also the orbitals, and there's a difference between orbital angle and nucleus angle, nuclear angle. Because even though the carbons may have a certain angle, the orbitals can be a little bit different from the atoms. That's also at play here. So that's why it happens some. But do you see why the rate is slower? They can't achieve 120. You predict it to be slower. Make sense? Application of understanding that. Okay. There's another application that's very important. Look down here. Remember, p orbital here. P orbital light. The effect of a p orbital being immediately adjacent to the reaction site. All of these on this row are much more reactive towards being substituted. The chlorine. Chlorine is a much better leaving group here than here. The reason is, all of these up here have a p orbital adjacent to the reaction site. That one's got 2. Doesn't mean they're both at work. Immediately adjacent to the reaction site. That's like saying there's a p orbital here, immediately adjacent to the reaction site. So, in the transition state, this becomes a p orbital. What can happen between these two p orbitals? They can interact during the transition state. The interaction is a good thing. It stabilizes the transition state by having one next door. If you stabilize the transition state, you don't have to draw every single thing I draw, right? You've already got this. What do we have over here? We have the SN2. Transition state, right? If we stabilize this, we lower it. So maybe it becomes like this. That's going to be an easier reaction. P orbital next door stabilizes the p orbital of the transition state. Does this guy have a p orbital next door? No. So it doesn't get the stabilization. It's not as reactive. These guys actually tend to be very toxic. Why? Because your body has DNA or proteins, and the DNA has things like amino groups. And the amine comes in here and kicks off that chlorine by an SN2. Pretty easy when it's activated. This substrate is much less toxic because it doesn't react as quickly with your biomolecules. Actually, in application, that's called propyl chloride. That's just called ethyl chloride. Anybody know what ethyl chloride is used in sports? Heard of that?
Numbing agent.
What?
It's a numbing agent.
Numbing agent. Yes. Have you ever seen, like in baseball, if a batter fouls a ball off his leg or ankle, he's like, ah.
It's like magic spray.
They come out and spray ethyl chloride. It's a gas, but it's compressed. When it comes out, it quickly evaporates and turns it cold, numbs it. Okay? Do you think they're spraying something highly toxic on the baseball player out there?
No.
No. You would never spray this on a baseball player. They would evacuate the stadium. These are much more reactive up here. Why? Hopefully I explained why. SN2 reactions can take place in the body, in the eyes. Your eyes have lots of proteins with nucleophiles. Halogens are good leaving groups typically, right? We're talking about the halogen being displaced by something. Okay? So there's a little bit of a look at the SN2 transition state. A couple of common things. Okay. We're sort of going to focus on SN2 for a little bit. Effective carbon substitution at the site of nucleophilic attack. The rate of these. That is, reacting these and substituting off the bromine. The bromine serving as a leaving group. Methyl bromide is the fastest. It's faster than that, that's faster than this, and this is faster than this. Slower, very slow. That's just kind of apparent. This is called a primary halide because the bromine is bonded to one carbon. No, that's different. Bromine can only always bond to one carbon. With halides and alcohols, when you talk about primary, secondary, and tertiary, you're talking about the carbon that it's bonded to. This carbon is primary. That carbon is only bonded to one, the one it's bonded to. The one it's bonded to here is bonded to 2, secondary. The one it's bonded to here is bonded to 3. So it's called a tertiary halide, but that's really referring to the substitution of the carbon that the bromine is on. Okay? Why is this one so much faster than that? Should we go to the transition state? Take a look at this. Don't try to draw this. You'll spend all your time just drawing. Look at these groups here. This is an ethyl and a methyl. Don't forget there's H's on there. And there's H's on here.
Can't get into it.
Ah, it can't get in there. It's like, hold on. It's going to be slow. Right? And the slow is in that K factor. That K hit, okay? But what if all this was just, what if this C only had H's, like that C? Now keep in mind, I drew the H's, but H's are quite small. Does it have any trouble getting in there? Oh, this is very simple, guys. The more substitution you have around the carbon, the more difficult the nucleophile is going to be able to get in there. Hold on, I can't get in there. There's too much in the way. This is called sterics. Steric hindrance. Okay? Steric hindrance negatively affects the rate of an SN2 reaction. So much that guess what? This guy is so sterically hindered, never do SN2 with a tertiary halide. Never. It doesn't happen, especially in this class. Never do it. It's too sterically hindered. Too sterically hindered. The model reaction was secondary, it wasn't tertiary. Never do tertiary. Now, while we're here, the above trend is just the opposite with SN1 reactions. What's the rate determining step of an SN1? Formation of the carbocation. Which carbocation would be best? Coming from...
Tertiary.
Ah! If that left, that carbocation would be best. The trend here is just the opposite with SN1, because this is going to make the better carbocation. When we get over to SN1, we're pretty much going to say never do it with primary. And that's what we said on the very first page. Remember we made a primary and we said bad, never do it? Yeah. SN1 is only going to be these two. You never do SN1 here. You're never going to make it like a methyl cation. So the trend is just the opposite. By the way, the SN2 rates, I think there's a table on the next page. This is back to SN2. This shows this being substituted with iodide. Lithium here, acetone solvent, SN2. Here's your rate. Methyl is known to be 163. Primary 1. Secondary slower. Tertiary, it's negative. And for us, we say never. No, never. Secondary tends to be pretty slow, but we'll do it. It's methyl faster, so there's some actual rates that came from experimental. Trip to the dentist. You can look, I don't show you any structures here, but you can look this up on the wiki. Anybody hoping to go to dental school? Or? Okay. Anesthetics in dentistry, very important. Makers rock like this. No? What, lidocaine, things like that? Okay. There's a variety of those anesthetics. You have short-acting ones that last maybe 10 minutes. Do a quick procedure, then the patient doesn't have to be numb all day. But then you have medium-acting and then long-acting. Maybe you want to do a 4-hour procedure and you, okay? Most of those, they last until the body metabolizes them. Short-acting ones get metabolized faster. So they get destroyed faster by the body. Well, the rate of that metabolism is based on, guess what? Sterics. It's around an amide. The ones that last longer are going to have lots of substitution around the amide. That slows down the hydrolysis of the amide. You can look at some of the structures, like these two, and you'll see. I think a cytokine has just more like groups. Okay? There's an application of sterics, slowing down the metabolism. Okay, leaving groupability. Oh, so what did we just talk about before? We were talking about sort of the whole substrate. A lot of we focused on maybe the site where the substitution takes place, the carbon. What about the leaving group? I mean, up there, why bromine? Could it be something else? Well, okay, well, let's look at that. The leaving groupability. We said halogens were better, but we said iodine is better leaving group than bromine, that's better than chlorine, and that's way better than fluorine. Typically, we only use these three as leaving groups in this chemistry. Rarely do you see a F being the leading group. For example, you do this reaction with iodine. Let's get rid of that, right? What's minus here? The oxygen. Okay. Instead of KOH, it's KOMe, O-methyl. Okay. We're looking to, the O-methyl replaces the iodine. SN2 or SN1? SN2, right? It's primary. We're not going to do SN1 here. SN2, get substitution. You show your spectator ion with the iodide leaving group. You try to do this with F. Very difficult to impossible. Easy. I would pretty much draw you an X right here. In general, we say that the iodine is a much better leaving group than the F. I mean, it left. It was able to leave. Poor leaving group. Not going to leave.
Why does it?
Well, which is more stable, I minus or F minus?
I minus.
Why is I minus more stable?
The size of the size.
Less electronegative sounds like it should be less stable because it doesn't like minus as much.
It's the size. It's massive compared to the fluorine.
We talked about this. The charge is more spread out here. It's a bigger atom, so the charge is more spread out. Remember, in the same group, size is important. Okay? We're using previous information. It's the same answer to this. Which acid is more acidic? HI. Why? Because it's more willing to become I minus than this. Okay? I'll say one thing here. I usually say at the end of the course. Trust your knowledge and apply it to other things. I mean, the reasoning that I try to give is usually universal. I'm not going to turn around and say, well, it's not more stable here. Then you would say, well, you said it over there. No, it's more stable here, the same reason we said over there. Trust your knowledge. Okay, so that's the trend. It's basically because of the stability of the anions. Iodine is more stable than bromide. Bromide is more stable than chloride. Okay. Usually these two are the best, iodine being the best. The problem is iodine compounds are more expensive, they're a little bit unstable. That's why bromides are often used, you see those more common. Now, chlorides are cheapest. The problem is the chlorides are not the best leaving group. So usually kind of the BR is sort of the balance between cheapness, cost, and stability. So that's why it's kind of most common. On industry, huge scale where they're worried about cost a lot, they'll tend to use chlorine more because it's just cheaper. But they're able to do it in a good enough rate. Okay, what other leaving groups can leave? What other atoms can leave in substitution chemistry? What about oxygen? What about oxygen? If you try to do this reaction with an OH here as a potential leaving group, and try to come in here and kick off that and get an OMe plus hydroxide, no reaction. The OH is not a good leaving group. No reaction. Hydroxide will not act as a leaving group as an LG in a slow rate determining step. Why do I say this in a slow rate determining step? That's because it will act as a leaving group in a fast step. Think about this. We've got two mechanisms, SN1 and SN2. Which step does the leaving group leave in these two reactions? How about SN1? The leaving group leaves in the rate determining step or fast step?
No, that's
Yes, rate determining step. What about SN2? So it leaves in the, yes. See, both of these mechanisms, the OH leaves in the rate determining step.
So it would have to be an SN1 reaction. The OH.
They both leave in slow rate determining steps. So why do I even say this? Because in organic 2, you'll see leaving groups leaving fast steps. If it leaves in a fast step, that implies that it's easier. So what I don't want to do is to just not include this and say, OH will not leave as a leaving group, and then you get over to organic 2 and it leaves. The difference is right here. In our reactions, it's a slow rate determining step, and I'm clarifying that. It can leave in a fast step. So that's why I added this clarification. But you should know which step it leaves in your mechanisms. Okay. OH will not leave, but water will leave. Water will leave in a rate determining step. How can we make this water? So OH. We can protonate it. If we take these electrons and react with the acid, include a strong acid, catalyst. If we include that, this can act as a base, and we can get that there. We can protonate the oxygen. H plus is called proton. Protonate the oxygen. Now, this is not a strong base. What's a strong base? Anions? sp3, sp2. That's not a strong base. So why are we able to do this? Well, guess what? This is a very poor equilibrium. The equilibrium is like that. It's a poor equilibrium. That doesn't mean we can't get some. And from here, the reaction can continue on. Now, if that thing connected to here is the leaving group, what does this look like when it leaves? Water. It's going to be H2O. Now a nucleophile, such as this, can now come in here and kick that off. What does this give? Well, it doesn't give that directly. Boom, boom. Now we have oxygen with an H and a methyl. That's positive now. Plus what?
water.
Plus water. The LG. Water will leave.
And then come back in the
Because when the oxygen leaves, what does this arrow mean? It takes on its long hair back and it becomes neutral water. Please follow your arrows here. Oxygen makes bond to carbon. There it is. There's the bond we make. We don't just magically lose H's. We've got to get rid of this H. What can take this H?
water.
Well, possibly, but there had to be a minus here, right? For example, what's your favorite strong acid? Mine's HCl. So how about Cl minus here? And if Cl minus is floating around, we can show it taking the H and leaving the electrons behind. What do we get?
Reform your
We
catalyst.
get that product. Plus what?
Your catalyst, so the HCl.
HCl reform. Catalyst. Somebody said water. Yes, you could also use water as the base to take the proton. You could even use methanol to take it. Because how does HCl exist in water? H2O plus. I promise to never say that again. So, this is a case where a neutral oxygen will not serve as a leaving group, but a positive oxygen will. That's a more broader way to look at it. Because when it wants to leave and become neutral. Protonate with a strong acid. We did an SN2. But then you say, well, hold on, I thought SN2 was just one step.
Substitution.
The substitution part was just one step. What was the first step? LG activation. Or biprotonation. So don't think that we did a two-step SN2. We had an activation step to make our leaving group good. How? By protonating it. No reaction up there. No acid. Here's something important. Why didn't I use the anion in the nucleophile? Why did I have to use the neutral? I think this may be on the next page. Yes. Very top. What's the problem with that reaction? Why not use the negative anion? Why did I use the neutral version of that? Because these two are not compatible. This is like hydroxide. That's OH minus, O methyl minus. That's a strong base. Well, that's an acid. You can't have strong base and strong acid in the same reaction. They're not compatible. So in the previous example, I used the neutral nucleophile, which is compatible with the strong acid. Okay, a common reaction of alcohols is to react them with HX, like HI. And you can replace the OH with the halide. We can convert an alcohol to an alkyl halide. If we totally balance this, we also get water. Show the mechanism for that. I give you a huge hint that you should already have known. HI is a strong acid, so it supplies H+. But it also supplies the nucleophile, I minus. While you're at it, predict the product for the reaction below. Predict the product of this reaction. Tomorrow at 2:30, we're going to have a review session here. Office hours here, 2:30 to 4. Anybody be here?
Sounds good.
Friday at 2:30, tomorrow at 2:30. I'll hold office hours here from 2:30 to 4. We decide what lab we're going to do on Monday, Tuesday. Shaken not stirred is a substitution reaction of alcohol with HCl. Williamson ether is a little bit more involved.
Do you recommend the shaken not stir?
Recommend what?
The shaken not stir? Sounds like you recommend the shaken not stir.
No, I mean, I don't know. My reaction?
What's your favorite?
No, it's just got a name, shaken not stir. I kind of came up with that because instead of doing it in a flask or a stir bar, you're doing the sub funnel and shake it. So it's shaken not stir. It's done in the sub funnel because it's just so fast.
Sounds like we need to do that one.
As soon as you combine it, it's done. So why put it in the flask and then it's done? Now put it in the sub funnel. So we just put it in the sub funnel directly.
What are you at? I'm willing to change my vote.
The Williamson ether involves reflux. The very last lab is the double E2 elimination, which is another change bond. Thanks. Change bond movie. Ever heard that one? You've heard of like Live and Let Die, Die Another Day, double E2 elimination.
Do you want to see
Which one?
the one benzene relation?
Is there any stereochemistry? You got your products? Is there any stereochemistry? Anything else to talk about? Do me a favor, if you stand up for a minute, for 5 seconds. All right. Do your arms like this. Real broad. Shoulders like this. All right. All right. Now you can sit back down. Okay. OH is a poor leaving group for both of these reactions. How do we make it a better leaving group? Protonate. Do we have a strong acid?
Yes.
Yes, we do. These electrons, every time you do an arrow, you say these electrons, right? These electrons react with H. And we can show the oxygen protonated, it now has a positive charge. A positive oxygen will be a good leaving group for this chemistry. Okay, the leaving group is on a primary carbon. Is our mechanism going to be SN1 or 2? 2. Boom, iodide comes in, kicks off the leaving group. These electrons do backside attack. These electrons move on to oxygen and become there. What does that give? That. That's it, it gives that. There's your mechanism. Protonation, and then do your good old backside attack. As we said, a common reaction of alcohols is to react them with HX and convert them to alkyl halides. We could have did this with HBr. We can also do it with ACl. A little slower with ACl because, well, we haven't covered nucleophile strength yet. Haven't covered that yet. Okay, how about the one below? In addition to OH groups, OR groups can also leave. That is, did that matter if that was H or R?
No.
It really does not matter. We called it water, but that's getting kind of specific. The bigger thing is we protonated the oxygen and it can leave. Same thing down here. Oh, what's going on down here? I've never seen such.
Protonate the oxygen.
Okay, as we move forward, you're going to see reactions, and you're like, you got to say, what's going on here? What type of chemistry can take place? By the time you get to the end of organic 2, you're going to have 20, 30, 40 reactions if possible. Final exam, nobody's going to tell you what reaction you're doing here. You got to be able to assess what chemistry can take place. Well, you guys know that the pi bonds in the benzene ring don't do anything with them in this class. That's nothing but alkane out there. You can't do anything out there but burn it. Okay? Burn it in your grill. But I have some long pairs, and I've got acid. What could you do? That's the only thing you can do. Now we have an oxygen there. I'm sorry, hydrogen there. Plus charge. There we go. We protonated it. One lone pair is now bonded to H. Okay? So I'm proposing a product here. What can happen next? I got Br minus. Could anything happen next?
So if we don't minus by kicks up.
What is it now?
We know a positive oxygen can serve as a leaving group. We got one. What's a good nucleophile? We haven't covered nucleophiles yet. For now, we're just going to kind of use it as a nucleophile. Okay. Someone have products here. Can I see what you got? Not right, but we'll talk about it. Not right.
No?
Not right. Not right. Somebody got it right? What you got? No products? Anybody got something that you think?
Is that wrong? I didn't.
Nope. Nope. Nope, you're all doing sort of the same thing. Anybody else?
Wait a minute.
Okay, please look back at the first page at the very top in bold. What does it say? I'm sorry, not the very first page is the outline, the typed outline.
Is it resonance?
Not a handout, something I typed. The outline.
What color is it?
No, it's in the blue, the first page of the outline. It was at the very top.
Tetrahedral carbon? Tetrahedral carbon?
Oh, tetrahedral carbon. Yes. And if you check the tape, I said that when we, yeah. Yes. This chemistry only takes place at tetrahedral carbons. But what? Okay. So, the leaving group, the oxygen, is attached to two different carbons here. Previous examples, it was only attached to one. Attached to two different carbons. Which one's tetrahedral?
The one on the right.
One on the right. That's the one you're going to do the chemistry at. Okay? We'll explain why, but now that we know that, let's do this. This attacks here and kicks the leaving group off of that tetrahedral carbon. And what does that give? It gives that, which was the Lg. Plus what? Plus ethyl bromide. Now you can draw this 101 ways. If you want to draw it like that, that's fine. It doesn't matter. If it's ethyl bromide, it's ethyl bromide. Right? Bromine now attached to that carbon, it's going, okay? However you want to draw it. There you go. What are we doing here? SN2. The nucleophile is kicking off at positive oxygen. Now the leaving group wasn't water in this case, because we had something else here. It's actually phenol. Phenol surfaces. It's phenol. Okay? Many of you attacked here and kicked off the ethanol. That's not a tetrahedral carbon. Why would it not happen? Because if it did come here, here's why. the weakest bond is going to break from that carbon. Which is weaker, the sigma bond to oxygen or the pi bond to carbon? Pi bond to carbon. You would have to be doing, you do something like this. And if you do that, you're no longer doing SN1 or SN2. You're kind of doing something else from organic 2. But for us, don't ever do that. You would never come in here and kick off the stronger bond. In the end, never, only attack tetrahedral carbons. All right? Now, somebody had a cation over here. Somebody had this. That's where you had it just leave. That's a bad cation. That's worse than like this. Because what's the hybridization of that cation? SP. But SP is supposed to be linear. That can't be linear. It's also not resonance stabilized. A lot of you guys think that's resonance stabilized. There's no resonance there. You got 6 p orbitals all lined up all the way around, okay? There's 6. If you're going to make a new one here, it's going to be perpendicular to these 6. Okay? Bad cation. So don't do SN1 either. But if you just remember that none of these reactions occur only on tetrahedral. So just knowing that, just never do anything here. So there's your outcome. Please don't think that this oxygen can't be served as a leaving group. You make oxygen a better leaving group by making it positive. That's just what we did here. Okay, what's next? There's another way to make OH a good leaving group. It's a little bit more involved. We can convert an OH to a tosylate. 4 variations of this, called mesylate or triflate. Here you actually make a new compound. Here, we converted it to a good leaving group in the mechanism. We didn't actually isolate the thing with a better leaving group. Here we're going to isolate the thing with the better leaving group. So it's an actual synthesis. Tosylates are the most common. Those are the ones that are at the introductory level, should be in your textbook, any textbook you're using. There's variations of this here. These are actually a little bit more common in the research lab. Maybe not. What's a tosylate? Instead of OH, okay, instead of OH, we have O. This is a sulfone, sulfonyl. How do we get this name here? Benzene with a methyl is called toluene. You can buy it at Lowe's, in the paint section. Toluene sulfonyl. And if it was an anion, it'd be 8. Toluene sulfonylate. Over the years, it's been shortened to tosylate. Okay? Everybody see it? Everybody with me? Toluene sulfonyl tosyl. The tosylate is where it's an anion after it leaves. It's abbreviated, I abbreviated OTOS. That's actually not correct. It's more common, strictly correct to be OTS. I usually put the O in there and call it OTOS. Instead of a toluene out here, if it's methyl, it's called a mesylate. Methyl sulfonylate. If it's a trifluoromethyl, it's called a triflate. This is the one you need to know, and this is the most common in this introductory level. Let's look at these. I don't think it's here. This whole thing is the LG. The whole thing. That is, we can have a nucleophile, maybe like an anion or something, come in here and kick this oxygen off without it having to be protonated. So this gives what? The nucleophile now bonded to the tetrahedral carbon. And what did the leaving group look like? What's the charge of this oxygen now? I'm going to make the arrow very
Negative.
precise. What's the charge of the oxygen?
Negative. What?
How many lone pairs?
Oh. No, it has a new lone pair.
There's 2 there. How many now?
Now 3.
Now 3, and the charge is anion. This is called tosylate. Tyrene sulfonate, tosylate. Okay? This is a good leaving group. You don't have to protonate it. It'll leave in neutral. Why? Why will it leave but an OH will not? That implies that this is more stable than an OH. Why will this leave but this not?
Resonant.
Why is this more stable?
Resonance.
Resonance. Do you see the resonance? These electrons can move here. These can move up. You can actually also do resonance structure where you put the charge here. Okay? So this anion is really delocalized onto 3 oxygens. By the way, carboxylic acid is more acidic because the anion is delocalized onto another oxygen. Well, here you have the anion delocalized on 2 oxygens. So how acidic do you think something like this is?
Very.
Very acidic. And this can be organic, so this can be an organic acid. This is called a sulfonic acid. Okay? If this was an H here, it'd be tosyl acid.
What's
Very
the,
acidic because the anion is resonance stabilized. Hey, guess what? What if this was another OH? What would that be?
No, it's H2SO4.
That's sulfuric acid, H2SO4. Okay? This is just where we're replacing, making an organic sulfonic acid. Still very acidic. Look on your pKa table in the handout. I mean, lab manual. It's there. Very acidic, sulfonic. That is, the anion is very stable. The anion will serve as a leaving group without having to protonate it. Tosylate's a good leaving group. Those others are also. By the way, a couple of variations of this. Right? We had sulfuric acid. This is there. If you replace the H's with R groups, such as maybe methyl, this is called a diester of sulfuric acid, like this. And if this was just that would be sulfate. Well, this is called dimethyl sulfate. Diethyl sulfate. These are potent alkylating agents. Okay? Nucleophiles will come in here and kick this oxygen off. Just like this. Now, that's not a tosylate leaving, but it's a variation of the tosylate idea. Now, these are very cheap because they come from sulfuric acid. And actually, the phenacetin, the Williamson ether, uses diethyl sulfate. And you end up, your nucleophile there attacks here, kicks that off, and you end up adding an ethyl to your nucleophile. And if you add an alkyl to your something, you're said to have alkylated it. Okay? So I'll show you these because they're very cheap. You can buy these by the gallon. They're also very toxic because they're very reactive.
Didn't you say diethyl sulfate was also a carcinogen?
Very toxic. Yeah. Because it will react with your DNA, put ethyl groups on your DNA, and ethyl is an alkyl. It will alkylate your DNA. It will modify your DNA, that leads to cancer. That's tosylate. How do you make tosylates? Tosylates are made, purified, characterized. Tosylates are made by reacting the alcohol with tosyl chloride and a base, a pyridine. Pyridine looks like benzene, but it's got one nitrogen. And the nitrogen is, the lone pair is sp2, and it's got some basicity. It's a substitution reaction. Tosyl chloride. Okay, you don't have to write all this down. I'm sort of just explaining things. Tosyl chloride would be what? Well, tosyl is this, right? What do you think's here instead of? Okay, that's tosyl chloride. And to get this product, the oxygen is now bonded to the tosyl. The oxygen displaces the chlorine. But it ain't SN1 or SN2 because that's got pi bonds. And so you have an H and a Cl that need to be lost. That's HCl, so it becomes acidic. That's why the base is included. Okay, I'm not going to show that mechanism because it's not SN1 or SN2. Okay, questions about tosylates over here? At this point, we can look back at the very, very front of the blue. Model reaction over here. It says SN2. What's going on here? Well, look at 31. That's a mesylate. Similar to a tosylate. Good leading group, yeah? Good leading group. They're reacting it with this nitrogen compound. Good nucleophile. What's going on? That's a primary carbon, so it better be SN2, not SN1. This comes in, kicks off the mesylate. Now the nitrogen's bonded to the carbon. The nitrogen has to lose an H to go neutral. Why do you think they include a base such as potassium carbonate? To remove the H. Okay. Acetonitrile reflux, wow, 3 days, 72 hours. So there we go. Mesylate. That's what we just looked at. Okay, other leaving groups. Can nitrogen be a leaving group? Look at halogens, oxygen, nitrogen. Yes. As with oxygen, nitrogen can be a good leaving group if it's made positive. It's not going to leave on its own. In fact, the only leaving groups that will leave on its own are your halogens and your tosylate. Those are your good leaving groups as is. Protonated oxygen, that's another way to make it. Protonated nitrogen, look at this. This is a special reaction. It's called a Herzig-Meyer reaction. Okay. I thought they just sold furniture, but apparently they also do chemistry. Okay. Early. What is it? Who sells furniture? Somewhere on Rancher Road. Herzig-Meyer? I don't know. Herzig-Meyer reaction. Mechanism for this. Well, what's going on?
Need to protonate the nitrogen.
Okay, let's protonate it. We've got strong acid. That will give, I'm just going to draw that phenyl. Let's draw these methyls out as CH3. And protonate, positive. Okay. We got I minus. What happens next?
You need to attack the
Attacking methyl.
right side methyl though, not the phenyl side.
Well, that'd be an sp2 carbon.
Yeah, you can't attack there.
Yeah, this then attacks the carbon. It kicks off the positive nitrogen. And what do you get? Death. But if you look at this, if this is the main substrate, which it probably is, you've actually removed a methyl group, if you look at it that way. It's a way to remove a methyl from a tertiary main and make it secondary. That's just a by the way statement. The mechanism should be consistent with what we've been doing. We made the nitrogen positive. So can a nitrogen serve as a leading group? Yeah. It's rare. This is a rare example. It's got a name. But it should fit the general theme that we're developing. Harligmeyer, I think it's called. They're the ones that sell furniture. Can sulfur be a leading group? When will we end? Well, sulfur is a very good biological application. Many of you will go in to take biochemistry. So that's why I'm compelled to talk a little bit about such here. Okay? Yes, sulfur can. For example, in norepinephrine in your body can be converted to epinephrine. Now, over in Europe, they call these different names. What do they call these in Europe? Adrenaline. I'm sorry. Adrenaline and noradrenaline. Yes. Okay. But we call it over here epinephrine. Adrenaline's more of a generic. Okay. What does nor mean? Anybody know what nor means? Nor typically means something has been removed. That is, if you look at epinephrine and then you say nor, what's been removed? You see? Usually the nor means something's been removed from the non-nor. The methyl's been removed. Going this way, you put a methyl on. Your body does this. Using SAM, S-A-M. It's a complex molecule. But it's got a positive sulfur right here with a methyl on it. And to get this product, these electrons, the nitrogen acts as a nucleophile, attacks the carbon and kicks off the positive sulfur. This has to lose an H. Something in the body takes the H, like water, to go neutral. And we can get this bond by a good old SN2, and this using this biomolecule. Your body uses sulfur a lot as leaving groups and also as nucleophiles once we get over there. But just like oxygen and nitrogen, it had to be turned into a positive first before it would leave. Your body creates this. I mean, you can maybe do that. By the way, you can buy SAM at health food stores, Whole Foods or something. If you read it, it'll say it methylates things. Like this, it methylated it to help with your body to produce these things. Sometimes maybe your body is kind of depleted on this and you can't. Okay, there we go. A little bit of application here. You ever heard of mustard gases? Okay, right here. This stuff is bad stuff. Called a mustard gas. It's yellow, mainly because of the sulfur, and that's why they call it mustard gas. Very toxic. Why? These halogens are displaced easily by your biomolecules. But why? We said ethyl chloride was not, we spray this on baseball players, that's not toxic. Is there a p orbital next door to make this particularly reactive for SN2? No. Why is it so reactive? Because what happens is these electrons come in here and do this first. An internal reaction which sort of just takes place. What does that give? This is almost like back bonding or something, but it was internal SN2. It's an internal SN2. That can just happen. But it's driven by entropy because the molecule's breaking apart. Well, what did it create? A positive sulfur. A good leaving group. But also that's a three-membered ring. Now your DNA or any other which has like amino groups, come in here and kick this leaving group back off. And this is quite reactive. Not only because it's a positive sulfur, but because the three-membered ring is opening back up. It's like, I didn't want to be three-membered ring anyway, thank you. But this happens very easily, and then you start, okay? That's one reason it's toxic. Another reason is the fate of this picks up an H and you form HCl. And so now you got HCl in your lungs and stuff. It's another problem. Does this make sense? Then the bad news. Now some of these are used to treat cancer. Chlorambucil. Chlor, am, he's got an amine, am, bu, 1, 2, 3, 4, butyl. So that's some of the name, okay? It's called a nitrogen mustard. The same thing, this nitrogen can attack here, make a three-membered ring, get the same thing. Then biomolecules can start reacting. But if you give it in a controlled manner, you know, with cancer, you want to kind of kill the cancer. Problem is, some of these things aren't selective. If you can screw up the DNA of the cancer cell, it'll be good. And a lot of research is trying to make such drugs, which are called chemotherapy drugs, they tend to be quite toxic themselves. You know, in a lot of cases, they almost kill the patient because they're not that selective. But you see the same thing in some of your cancer drugs. Alkylating agents. Yeah. So that's an application of this. And ultimately, that's why we have organic chemistry, so then we can understand these type of applications. Okay, so that was shown below. Let's look at nucleophile. Because we've been focused on leaving groups, and that's the end of the leaving groups. I mean, what did we not cover for leaving groups? Actually, carbon. Could carbon be a leaving group? I mean, how stable is a C- going to be if it leaves? Yeah, very rarely. But there are some unique examples of carbon being leaving groups. There'll be some uniqueness to them that make it possible. Usually not. Hydrogen leaving group? No. We covered the leaving groups. What about the nucleophile? Okay, the thing that's doing the attacking. First thing, anions are more nucleophilic than neutral. Hydroxide is a better nucleophile than neutral oxygen. Just got more electron density. I remember something we didn't discuss when we showed the two mechanisms. we can understand why this would attack a cation. Why would it attack here, though? We kind of said it a couple of weeks ago. Why would it attack there? There's no cation there. Or what do we have here? No, we got a dipole. It's a partial plus here. So when we do SN2, it's attacking the partial plus. That's why it's coming in there. I didn't mention it, as opposed to this. What's going to be more attracted to a partial plus? An anion or a neutral? Yeah, the anion. The anion's a better nucleophile than the neutral. That's better than this. That anion is better than ammonia. That should make sense. Okay. Number 2. A less electronegative atom will be more nucleophilic or reactive. The lone pair will be. Because the lone pair is not held as tight to the nucleus. This is what we said before with acid-base chemistry. For example, which is a better nucleophile, ammonia or water? Well, they're both neutral, so that's not the answer. Ammonia, why? Well, because of that right there. Which atom holds the electrons tighter?
Oxygen.
Oxygen. Oxygen holds the lone pairs tight. Ammonia, not so much. Ammonia lets its lone pair get out there and do backside attack. It lets its lone pair get out there and do stuff. Oxygen holds it tight. That's the same reason this is a stronger base than that. So there's correlation there. Stronger bases tend to be stronger nucleophiles. Okay, let's look at that down here. H2S is a better nucleophile than water. Why? Because oxygen holds the lone pair tighter. Sulfur less electronegative. The lone pair is more out there looking to do backside attack. Your body actually uses sulfur as a nucleophile all the time. Because even in the neutral, it's a good nucleophile. I minus is a better nucleophile than F minus. F minus holds the electrons tighter. Bad parents have reactive kids. All right? Bad parents have reactive lone pairs. They don't hang on to the kids there. But sterics are important. Remember how the sterics around the thing with the leaving group? You know, if you got sterics around here that the nucleophile can't get in, it's like, well, you know, there's H's here. Remember all this? This was sterics on the thing with the leaving group. What about sterics on the nucleophile? Well, it's just as important. Because what if the nucleophile had lots of sterics? Maybe like a nitrogen with lots of groups on it. You can have sterics over there as well. Look at here. The primary mean is more nucleophilic than the secondary, and it's more nucleophilic than the tertiary. That's just the sterics on the other reactor. Makes sense, yeah? Good. Okay. Here the substitution is on the nucleophile. 2 things on the nucleophile. 3 things on the nucleophile. By the way, the tertiary means tend to be so sterically hindered, they're usually not good for SN2. And very often we use them as basis for E2 reactions because they won't do SN2. Too sterically hindered. You can also have substitution not on the nucleophilic atom, but on the atom next door. And that's what these examples are showing. The carbon next door. So this is a better nucleophile. I mean, they're both oxygen anions. The difference is this has less sterics. Now you can also have more and more sterics out here. Of course, the further away you get, the less it's going to influence things. By the way, what's the difference between a base and a nucleophile? What does a base attack? An H.
The atom.
Yes. What does a nucleophile attack? Anything else? So if this attacks this carbon, we call it a nucleophile. If this attacks this H, we call it a base. Judging them is pretty consistent. One key difference, though, is sterics usually don't influence acid-base reactions.
Because hydrogen's so small.
Because H is so small, even if I'm sterically hindered, that H can just come near me because it has no hindrance. Sterics influence nucleophiles, but not bases. That's why the triethylamine up there is a good base, but it's a bad nucleophile. Because sterics. Okay. Some of these others should be pretty intuitive from what we've talked about before. For example, resonance. This is a better nucleophile than this. They're both oxygen anions, or are they? This is a pure oxygen anion. Is this oxygen really fully minus? It's delocalized. So it's only a partial minus. We got to know that that resonance stuff is there. And that that's not a truly informative structure. Full minus on oxygen, only partial minus. Better nucleophile, yeah? Agree? Over here, which is better nucleophile? Same thing. That lone pair is sitting on that nitrogen. This one is delocalized into the ring. By the way, I sent out the resonance answer key to a few. Some of you asked questions about it. Hopefully you got your answers from the key. If not, please ask. Making sense here? Hybridization effects. See, a lot of this is acid-base chemistry. Which is a better nucleophile? Well, obviously this one. Why? This lone pair is in what type of orbital? sp3. Pyridine, we used for before. That's pyridine. What type of?
SP2.
sp2. Which lone pair is out there more to react? sp3. This lone pair is held tighter to the nucleus. So that nitrogen's a better parent than this one. Right?
Mm-hmm.
We're using previous knowledge to this. Here we go. Do these on your own, and we'll look at them tomorrow. Rank each group. Weakest to strongest. Weakest to strongest here. Weakest to strongest here. Nucleophiles. Summing it up. What type of nucleophile can participate in an SN2 reaction? We haven't really stated this. So it's not really a summation yet, but okay. What type of nucleophile can participate in SN2?
It's gonna be
The answer is a strong one. Only strong. Why only strong? Now with SN1, it can be strong or weak. Why only strong for SN2?
Because it has to kick off the leading group.
That's mostly right, but what's the statement though that?
Part of the rate determinants.
Hey! Say it again.
Part of the rate determinants.
Because in SN2, the nucleophile is involved in the rate determining step. That's the hard step. It's got to be strong to do that. Is the nucleophile involved in the rate limiting step in SN1? No. There's the fast step. There's the easy. And if it's easy, you can have any type of nucleophile, strong or weak. Strong ones. Written up there. Which ones are strong? The same as for bases. Anions?
It's gonna be SP3.
Not tertiary mean because it's sterically hindered. Sterics make it not strong.
SP3.
Anions, sp3 nitrogens, sometimes sp2, that's borderline. But remember, sterics can make that no good. Like a sterically hindered anion is actually not a good nucleophile. So remember sterics there as well. But it's the same as bases. But remember, bases don't, sterics not in effect. So we didn't ever say that about bases. But for nucleophiles, same thing, except sterics is important as well. Okay, please look ahead. There's some things to do. I'll assume you did at least this page or a little bit more, and we'll hit them running tomorrow. Question for you, please.
Can we just quickly vote on which
Or can you just tell us which one we ought to do?
Yeah.
Based on your experience.
Okay, this is what I'm thinking. Since you asked, I'll go ahead and try to make a decision. I'm thinking, once I let the cat out of the bag, it's going to be, there it is. No lab on Monday or Tuesday. We're going to concentrate on the test.
Oh.
We're going to have lab on Wednesday, Thursday. Okay?
Do you still want our group reports on Monday, Tuesday, or can they
Yes.
come in? Okay.
Yes. Is this okay?
Yeah.
Okay? I was toying with canceling the Wednesday, Thursday lab, but I decided to do it this way instead so you can have the time for the test. But we'll have lab on Wednesday, Thursday. That will be the very end of the course. So we've got to have lab then. Then that one involves elimination, and I would be open to, if you don't want to do elimination, we have 4 to consider. Probably would not do the Diels-Alder because we need to do at least 1 substitution or elimination. The elimination would involve using your dibromide you made earlier. Okay, sorry. This is, we're really not there yet. This is the elimination. If you want one a day, pick it up. Sorry I didn't pass them out earlier. I'll leave a stack here, however you think's best. Only take one. I'll pick up the stack going around. Have a good day, guys. See some of you this afternoon.